Right, so today we're going to start looking at trig, and we're going to just focus today on what an angle is, how you measure it, mainly degrees or radians, and how you convert between the two. Okay, so just a quick review of what an angle is. So an angle is basically made up of two rays that have a common vertex. That vertex is the starting point for each of the rays. And when we talk about angles, sometimes the sides of the angle won't be rays. For example, if you have a triangle, there's segments. All right, so this is this is the geometric definition of an angle that you can see in any geometry book. But keep in mind that sometimes an angle in a triangle, it's not made up of rays, it's made up of segments. Okay, the two rays, they form the sides of the angle. Okay, and the sides have special names. One side is called the initial side. The other side is the terminal side. Okay, and the way you figure out which side is initial and which side is terminal is we move in a counterclockwise direction, starting at the initial side, going towards the terminal side. We're also going to come up with a way to draw an angle where we always put the initial side in a certain spot. So that way it makes it really easy to figure out. Okay, so here's our angle. Okay, and the arrow in red, that's going in a counterclockwise direction. So the initial side is the one on the bottom, and then counterclockwise you head towards the terminal side. That's the one at an angle. Now, really, we have two different angles here. You have this angle between the two rays, okay, inside, and we also have an angle that's outside the two rays. Okay, generally, when we talk about an angle, we're talking about the one that's between the two rays. Okay, in other words, the one that's smaller than 180. Generally won't be referencing the one on the outside of the two rays. Hey, any questions on what an angle is, what it's made up of, what the sides are called, or how you determine which side is initial and which side is terminal? So when we start to solve for angles in a triangle, there's different letters that we'll use. Okay, you saw one in the video. Anybody remember what the name of the Greek letter they used was? Had like a circle and a horizontal line in the middle. Yeah. Theta. Theta. Yep. Theta. So yep, the fourth one here, that's theta. Anybody know the name of the first one? The first letter in the Greek alphabet, that's alpha. Okay, how about the second one? Kind of looks like a B. Yep. Beta. Yep, that's beta. And the one here looks kind of like a Y, but one side is a little bit more curved and the other one's straight. Or maybe it looks like a bird. Anybody know what that one's called? Okay, that one is gamma. That's gamma. Theta, we just mentioned that one. And how about this one? Looks kind of like a W. But it kind of curves back in on the middle of itself. Yep.
Isn't that the lowercase omega?
That's a lowercase omega. Yep. Versus a capital omega, you might have seen that before. Looks kind of almost like a horseshoe kind of, except the bottom part is flat. But these are different letters that we can use to represent angles. A lot of times we'll use theta when we only have a single angle to represent. But when we have multiple angles, like in a triangle, we'll use alpha, beta, and gamma. Okay, so they're just letters. They're just variables that represent, for us and for our purposes, angles. All right, so when we sketch an angle, it'd be nice if we had a way to sketch it so that everybody's sketch would come out similar. Okay, because if I said sketch a 45-degree angle, there's a lot of ways you could do that. Okay? Any angle that measures 45 degrees would fit the description of what I'm looking for, but you all might draw it a little differently. Okay, some of you might draw it like that. Someone else might draw it turned, okay, like that. So what we have here is standard position. Okay, standard position gives us a way to draw an angle so that if I said draw a 45-degree angle, everybody should look pretty similar. And two things have to happen for an angle to be in standard position. First, the vertex of the angle has to be at the origin. And second, the initial side is on the positive x-axis. Okay, so in red there's an angle in standard position. Okay, now if I took it and went like that, is that still in standard position? Nope, what's wrong with it this time? Yeah, the vertex is not at the origin. The initial side is still where it should be, but the vertex isn't. Okay, let's say I did something like that. Okay, is that in standard position? No. Nope, what's wrong with it now?
It's not on the x-axis.
Right, the initial side is not on the x-axis, even though the vertex is at the origin. Right? So both of those things have to happen for it to be in standard position. Okay. Any question on that? All right, so one way that you can measure an angle is you can use degrees. Okay, and even if you use degrees, there's different ways to do that. We're generally going to use degrees that have an integer part, okay, and then we'll have a decimal part, maybe like 45.736 degrees. Somebody else mentioned earlier, you can also do what's called degrees, minutes, seconds. Right? You can think of minutes and seconds as fractions of a degree, just like minutes and seconds are fractions of an hour. Okay? So you could say you have 2.5 hours, or you could say 2 hours and 30 minutes. Same thing. Whether you can use degrees, minutes, or you could use a decimal. Okay? Generally, we're going to use the decimal. If you have one complete rotation, okay, kind of going all the way around in a circle, that would be a 360-degree angle. All right, so if you had a 360-degree angle, what would you think would happen between the initial side and the terminal side if you were to sketch that? Yeah.
It would look like just one, right?
Yeah, it would look like they're at the same point. Okay, so here's an example. We'll talk more about what this circle is called in a little bit. It has to do with a unit circle. Okay, and as you drag that around, the initial side is in black, and that always stays on the positive x-axis. The terminal side is what's moving. Okay, so now that's 180. It's 270. And if we go all the way around, that's 360. All right, so the initial side and the terminal side, they're right on top of each other. Any question on that? Now you might be noticing this, this 2 pi here. That has to do with radians. Okay, so we'll talk about how would you get that. Okay, 360 is 1 revolution. It's also the same as 2 pi radians. Okay, so we'll get to that in a little bit. Since we'll be using the terms clockwise and counterclockwise a lot, We'll just abbreviate them. Counterclockwise, CCW, and then clockwise, CW. Okay, what would a half counterclockwise revolution be? How many degrees would that be? Yeah.
180?
Yep, 180. How about a quarter revolution counterclockwise, Jeff?
90.
Yep, that'd be 90. So all the angles that we just did there were all counterclockwise. And if you're going to measure an angle that's counterclockwise, that's positive. There's also another direction we can measure angles in, and that's clockwise. All right, so I'll pull that diagram back up and show you what happens if you start to go and bring the terminal side, okay, the other way. All right, so let's bring it back to 0. And then if we start going the other way, now we can get a negative angle. Does anybody see another way you could end up with the terminal side exactly where it is, but instead of writing it as negative 90, think of a different way you could write it? Think about maybe changing the direction. Would negative 90 be the same as? Yeah.
270 counterclockwise.
Yeah, just positive 270. So negative 90 and positive 270, if you sketch the angle, you can't tell the difference between the terminal side. It'd be exactly in the same spot. Okay. You can also measure angles that are larger than 360. Okay, typically this happens when we talk about rotations or if something's spinning. When you're dealing with a triangle, would you ever have an angle larger than 360? In fact, what would be the maximum, if you know a little bit about triangles, the maximum size angle that you could have in a triangle? Yep.
It has to be less than 180?
Yeah, less than 180. So like 179.9 repeating. You could have an angle, you know, very big in a triangle if it was something like this. Okay, those two angles could be very small, then the one at the bottom could be very big, but it can never exceed 180. If you have an angle that exceeds 180, then you don't have a triangle. Okay? So 360, that's a pretty big angle, not an angle we'd ever really be talking about with a flat triangle. Okay, but if we start to go around more than once, now we can see that that's a 450-degree angle. What's that the same as? If you wanted to maybe write it as a smaller number, how do you see what 450 would be the same as? Think about if you didn't go around that extra time. I could have stopped where? And it would have been right there. Yeah?
90 degrees?
Yeah, it's the same as 90. Okay? Same as 90. And you could go around as many times as you want. You can have a lot of fun with that. You get 2,970 degrees, which is exactly the same as 90 and all the other angles. So there's a pattern. Yeah, it's kind of fun. So there's a pattern. You can just keep adding revolutions, and you get right back where you started. Okay, adding a complete revolution doesn't change where the terminal side would land. Right? And we'll talk more about, there's a word for that in a little bit. Coterminal. So two angles are coterminal if they have the same initial and terminal sides. So if you want to find two angles that are coterminal to each other, all you have to do is take your angle and add 360, or subtract 360. As many times as you want. that'll give you an angle that's coterminal. Now, the adding or subtracting 360, that assumes that you're working in degrees. If you're working in radians, you'd be adding or subtracting multiples of 2 pi. Okay, but we'll talk more about that. Okay, so again, coterminal. Angles that have the same initial and terminal sides. Right, so let's just take a look. If we do it in the negative direction, so we can see that that was the same as positive 90, okay, or negative 270. And if you just take negative 270 and subtract 360, that tells me where it would be if I went around one more time, negative 630. Okay, right there. And then I could just keep going. Okay, so negative 630, negative 270, positive 90. Those are all coterminal angles. All right, so let's try making a sketch. I'll give you an angle. We're not going to use a protractor to measure it perfectly. I'm just going to be looking for a rough sketch of an angle. And then I want you to name one angle that would be coterminal that's positive, and another angle that's coterminal and negative. Okay, so remember, the only difference between positive and negative is whether you add or subtract 360 and make it a positive or a negative. Right, so 30 degrees. Okay, one reason we start out with degrees is exactly for this kind of problem. Most people can visualize a 30-degree angle. But if I said to you pi over 6 radians, unless you're really familiar with radians, you might not know how big pi over 6 radians is, because it's going to be a new thing. You haven't really worked with it a lot. So how would you describe the size of a 30-degree angle? Like, what quadrant maybe? You could say what the terminal side is going to be in. And then is it more than halfway towards the 90 in that quadrant? Is it less than halfway? What do you think?
So it's going to be in the first quadrant, and it's a little bit less than halfway.
Yeah. So let's sketch. You know what? Let's make that a different color. Okay, so there's my initial side. Okay, I'm just going to start that on the positive x-axis. Why did I put the initial side there? There's many ways you could draw a 30-degree angle. It said standard position, so I have to put it there. Okay. Same reason why I started the vertex at the origin. Right, and then 30 degrees, you know, might be about like that. Okay, and let's name two angles that are coterminal with 30. Anybody give me a positive angle that would be coterminal with 30? Justin? Yep, 390. And how'd you get that? You just add 360. So it's going to bring you right back one revolution around. And then maybe a negative angle? Yep.
Negative 330.
Yep. And how'd you get that one?
Subtract 360 from 30.
Yeah, you just subtract 360. Right. So that's all they want. Okay, let's try 145. So let's start just by doing the initial side. We don't really have a choice about that. And what about the terminal side? Anybody explain where the terminal side is going to be? Oh, Brandon, can you tell me where the terminal side would be?
It's going to be in quadrant 2.
Okay, it's going to be in quadrant 2. To be a little bit more specific, is it going to be at the halfway point, more than half or less than half? Less than half? All right, let's think about it. So if you go straight up here, this is 90. If you go over here, it's 180. What would be exactly halfway between 90 and 180? In other words, what's the average? What's right in between?
135?
Yeah, 135 is right in the middle. So that's going to be a little more than half. Okay, 145, a little more than half. So we'll draw it maybe about like that. Okay, so there's our angle in standard position. And now we'll get two angles that are coterminal. Let's see. So take 145, add 360, get 505. Don't forget your symbol because it's in degrees. And take 145 and subtract 360, negative 215. Okay, I'm not going to have you sketch an example going around more than once. The way that this program does it is it just adds that spiral in so you can see how many times you've gone around. Otherwise, if you don't put that spiral in and you just show the initial and terminal, there's no way you'd know how many times you went around. Okay, and let's try a negative. Okay, where's my terminal side going to be this time? Which quadrant? Oh, Michael?
Quadrant 4.
Yeah, it's going to be in quadrant 4. And can you describe kind of the halfway point, more than half, less than half?
Halfway?
Yeah, it's going to be exactly halfway. Each quadrant is 90 degrees. So negative 45 splits the quadrant right in half. Or another way to think about it is the slope of that terminal side. It's negative 1. Okay. And let's find two coterminal angles. Okay, Taylor, could you give me a positive angle that would be coterminal with negative 45?
315.
Yep, add 360 and you get 315. Okay, subtract 360, you'd get negative 405. Okay. Any questions on coterminal angles? So an angle can be classified depending on its size. Anybody tell me the definition of an acute angle? What is an acute angle? Josh?
Angle less than 90 degrees.
Okay, yeah, that's partially true. An angle that's less than 90. But there has to be something else too. For example 1C is not acute, even though it is less than 90. Yeah?
Greater than negative 90?
No, not greater than negative 90.
Greater than 0.
Greater than 0, yeah. So an acute angle is a term that, the way our book defines it, only applies to positive angles. So more than 0, but less than 90. Okay, a right angle. Brian, what's a right angle?
90 degrees.
Yeah, it's exactly 90 degrees. Again, obtuse angle. What would be the range of angles that would be obtuse between what and what? Yeah, Masan?
0 to 180.
0 to 180? Not quite, because keep in mind an acute angle covers everything from 0 to 90.
Oh, I mean, 90.
Okay, 90 to 180. Yep. Now all of these terms apply to a single angle. Acute, right, obtuse. Then we can get into some terms that describe a relationship between two angles. Okay, the first one is complementary. Okay, so this is a term that it only applies if you're comparing two angles. And there's a special relationship. Anybody know what would make angles complementary? And it's a little tricky here. There are the two parts like we had before, like for an acute angle. But go ahead, Josh.
Two angles that add up to 90 degrees.
Okay, they do have to add up to 90. And one more thing. And you know the other condition on that? Because I can think of two numbers in my head that add up to 90 that would not be complementary. If I give you the example, then you'll know the condition.
They have to be positive?
They have to be positive. So for example, a negative 10 and a 100-degree angle, those are not complementary. Not according to the way our book defines complementary. They said it has to be positive. Okay, all these terms are on page 318, if you need to see any of them. And what about supplementary? Oh, Shannon, think you could tell me what supplementary?
That add up to 180.
Yep. Two positive angles, this time they add up to 180. Now there's no condition on these angles actually having to be touching. Okay, sometimes in geometry we talk about what's called a linear pair. Angles that are adjacent and add up to 180. But if we could take these two angles, take one like that. Let's take one like this. And if we take those two angles and move them apart, okay, the blue and the green angle are still supplementary, even though they're not touching anymore. They're not a linear pair, okay, because they're not adjacent, but they are still supplementary. They still would add up to 180. Okay? And if you turn it, and, anything like that, they're still supplementary. Right, so negative angles do not have complements or supplements, based on the definitions we just went through. Right, let's take an angle, see if we can find the complement and supplement. Okay, what would be the complement to a 48-degree angle? Be the comment. Nick? 42 degrees. Good. So basically, if you just find out 48 plus what number would give you 90. Okay. And how about the supplement? Yeah.
132.
What is it?
132.
132? Okay, we can always check our answer just by 132 plus 48 adds up to 180. What's the complement to negative 18? Complement to negative 18. Josh? Yeah, there is none. How about the supplement? Yeah.
Isn't one?
There isn't one. Negative angles do not have complements or supplements. Right, and how about x? Okay, assume here x is a positive number. If it was a negative, obviously the answer would be none. What's the complement to an angle that's x degrees? Yeah?
90 minus x.
Okay, good. 90 minus x degrees. And the supplement? Yeah?
180 minus x degrees.
180 minus x degrees. Okay, so any questions on complements or supplements? All right, there's actually kind of a cheesy math joke. You want to hear a cheesy math joke?
Sure.
All right. So it's perfect because it ties in with angles and everything we're doing right now. So anybody cold in here today? Anybody cold? Yeah, somebody has to say they're cold. You're cold? Well, if you go sit in the corner, it's 90 degrees. Isn't that good? Yeah. Isn't that an acute joke? Yeah. There you go.
You did it twice.
No, Mr. Hager, we're all just obtuse for you guys.
All right, so let's look at another way we can measure an angle, which is in radians, and my joke wouldn't work in radians, so it's a good thing we already did it. But radians, it's just another way you can measure an angle. It's not very difficult. You just have to know a little bit about how to convert between degrees and radians. All right, so first thing we'll take a look at in this picture. Okay, I've drawn a circle, and I've drawn what's called a central angle. Okay, that's an angle that it's drawn inside a circle. The vertex is right at the center. And what happens in this angle is the two rays, they come out and they intersect kind of the circumference, or they intersect the perimeter of the circle at 2 points. And this arc between A and B, that's called an intercepted arc. Not sected, but intercepted arc. And the way we can denote it is you write AB and you put a curved segment above it. That means arc AB. So I'm going to show you visually what a radian would look like. Okay, so this is more of a geometric definition of a radian. So angle ACB would be 1 radian if arc AB would be the exact same length as the radius. So if you draw an angle in a circle and the intercepted arc comes out to exactly the same length as the radius, then you have an angle that's 1 radian. Any question on that idea? So if you took a piece of string, laid it along that red arc, then straightened it out, measured the radius, comes out the same, your angle is 1 radian. So you can kind of see the connection here between the word radian and radius. Okay, there is a bit of a relation there. And in fact, to figure out how many degrees are in a radian, we're going to use a circle again. Okay, but we're not just going to use any circle. We're going to draw a special circle. Okay, it's a circle that has a radius of exactly 1. Okay, if you draw a circle that has radius 1, that's called a unit circle. And I'm going to tell you a fact about a unit circle that for now you're just going to have to trust me that it's true. Okay? And we're going to use that fact somehow to figure out how many degrees in a radian. Okay, so there's a special thing that happens in a unit circle. Okay, in a unit circle, if you measure the central angle in radians, okay, not degrees, but if you measure the central angle in radians, it comes out exactly the same as the length of the intercepted arc. So in other words, if you can find the size of the arc, you know the size of the angle, because they're the same. And that's a circle. So we have formulas for working with circles, specifically the circumference of a circle. All right? So in a unit circle, if you can find the measure of the intercepted arc, then you can automatically find the measure of the central angle. They come out the same. So what we need to do is somehow draw an angle in this picture that we know the intercepted arc length. So we can't just draw any angle. If I just did, say that, I don't know what that arc is. Anybody have a thought about what kind of angle we could draw in the circle? And it would make it very easy to find the length of the intercepted arc. Yeah?
90 degrees or 180 degrees?
Okay, why? What's 90? Yeah, you could use 90 or 180. Can you describe what those are?
That would be the half or quarter of the circle circumference.
Okay, so if you did a 90 or you did a 180, as long as you know your formula for the circumference, you could divide by 4, and that would give you a quarter circle, or a half would give you a half circle. But let's say I didn't want to divide by anything. I just wanted to use the formula for circumference. What kind of angle could I draw?
360-degree angle?
Yeah, if you draw a 360-degree angle, which is where the initial side and the terminal side would be right on top of each other, so it would look just like that. The intercepted arc would be the entire circle. So it's no longer an arc, but what do we call it when it's an arc that goes all the way around and makes a full circle? You know the name of that, Nick? That's a circumference. Okay, so as long as we know how to find the circumference of that circle, whatever that comes out to, that's the measure of the angle we just drew in radians. Okay, so we've got one revolution, which is the same as 360. Now we need the formula for the circumference of a circle, so we can find the length of that arc. What's the formula for the circumference of a circle? Remember that? Sometimes you can write it with either a radius or you can use diameter. I think radius here would be easier because that's what we know. Yep, 2 pi r. Okay, so circumference equals 2 pi r. What's my radius in this case? 1. So the circumference of my circle is 2 pi r. 2 pi times 1, or the circumference is 2 pi. That's the circumference. But what did we say earlier up above? The circumference is the same as what? In a unit circle. Remember, the circumference is just an arc. Yeah?
Well, we said that the radian measure of the central angle
Yes.
is the same as the length of the arc.
Yep. So the radian measure of the central angle is the same as the length of the arc. Well, we know the length of the arc is 2 pi. So the radian, if you measure the central angle in radians, it is also 2 pi. So that tells us that if you have an angle that goes all the way around, okay, makes a full revolution, 360. 360 degrees is exactly the same as 2 pi radians. Okay, and that's assuming that this fact we have up above is true, which it is. So we can say that in 2 pi radians, that's 1 revolution, that's the same as 360 degrees, or we can reduce that a little bit. And we can say in pi radians, there's 180 degrees. So that's the conversion between radians and degrees. In pi radians, there's 180 degrees.
So you can use that for every circle?
Yeah. You can use that to convert any number of radians to any number of degrees. Now, one way to do it is you could set up a proportion. You could say in pi radians, there's 180 degrees. And then if I say in 8 radians, there's how many degrees? So you could do it like that. You could set up a proportion, but that's it's basically the way we're going to do it, but we're going to come up with a simpler way to think about it without using a proportion. When you have a conversion factor, what number is usually involved? And it makes the conversion easy to do. Yeah.
Conversion factor?
Yeah, what number is normally involved when you convert, say, feet to inches or minutes to seconds or, you know, days to years, anything like that? Usually, what number? A 1. So we say in 1 foot is 12 inches. In 1 hour, 60 minutes. In 1 day, 24 hours. But there's always a 1 involved. Okay. Well, let's take this equation and let's get a 1 involved. Okay, so divide each side by 180. Not 180 degrees, just 180. And that leaves me with 180 divided by 180, which is 1 degree, equals pi over 180 radians. Okay, so this is the conversion that I think of in my head when I want to convert degrees to radians. So if you told me, okay, what about 7 degrees? Just multiply each side by 7. 7 degrees is 7 pi over 180 radians. If you said 12.6 degrees, multiply each side by 12.6. Then it would be 12.6 equals 12.6 times pi divided by 180. So the short way to explain how you do that is take, if you're changing from a degree to a radian, pi's on top, 180's in the bottom. You multiply it by pi, and you divide by 180. Okay, that's exactly what this formula on the other page is doing. So if you want to convert degrees to radians, multiply by pi, and divide by 180. Okay, let's look at radians to degrees. It's going to be very similar. Okay, let's take our original equation again. This time, how would I get a 1 on the left side instead of on the right? Yeah?
Divide by pi.
Just pi.
Yeah.
Yep, no unit on that number, just pi. So now we get 1 radian equals 180 divided by pi degrees. So if you said, well, how many degrees in 5 radians? Just multiply each side of this equation by 5. 5 radians, 5 times 180 divided by pi. Multiply by 180, divide by pi. That's how you change a radian to a degree. So now if you wanted to get an idea of how big is a radian, take 180 divided by pi, and that'll tell you how many degrees it is. It's 180 divided by pi. It's about 57.3 degrees. About 57.3. Okay, any questions on that? Okay, so we'll practice converting. Okay, as we go through, I'm going to point out a couple things that can come up. Okay, first thing is when you're converting a degree to a radian, there are certain angles that we will not round the answer off to decimals. Okay, if your angle that you're starting with is a multiple of 30 or 45 degrees, generally we do not round those answers off to decimals. We leave them as fractions. Okay? And you can see that in this diagram. Okay, so 0 radians is the same as 0 degrees. So notice it's all decimals, all decimals, all decimals, till you get to, if I can get it right on 30, you can see it. 30 is pi over 6. Okay, this is the one we're going to do in a second. Okay, let's look at 45. 45 is pi over 4. Then all of a sudden you go off 45 and they start using decimals again till you get to 60. It's pi over 3. And then up to 90, it's pi over 2. So if your angle is a multiple of 30 or 45, we're going to leave the answer in terms of pi. All right, so let's see how they got pi over 6. Okay, so when you're converting, every time you're either going to multiply by pi over 180 or 180 over pi. Okay, and they're very similar, so you got to try to remember which one is which. Okay, the way that I remember it, right now, think of this as a fraction. You've got degrees in the top. You're trying to change to radians. Where would degrees have to go in this other fraction to cancel degrees out in the first fraction? Yeah? In the top?
Yeah.
So think about if you had like an x in the top of a fraction times another x. That would give you x squared, right?
Yeah.
So if you put degrees in the top times degrees, you're going to have a unit of degrees squared, which I don't know what that even is. So that's okay. But we've got to figure out where else could we put it besides the top? The bottom. So now if you think of something like this, x in the top, x in the bottom, they cancel out. It works exactly the same way with units. Degrees in the bottom, radians in the top. So now we just have to decide which number goes with which. On the other page, what was the number that had the degree symbol on it? Was that the 180 or was that the pi? That was the 180. Okay, if you go back, 180 had the degree symbol, pi was radians. So now I don't even have to memorize, is it pi over 180 or 180 over pi? I just think about where I want the units to go to cancel. And then remember, 180 always goes with degrees, pi goes with radians. So cancel your degrees. And how about 30 into 180? How many times does that go? Yeah.
6.
6. Goes in once, goes in 6, and you're left with pi over 6. Question on that? Any comment about how I wrote the final answer? Anybody?
Label that as radians.
Okay, so there's no label there, right? When you're working with radians, you don't have to label it. I did on the first problem just to try to kind of help you out a little with the units, but in general, if your answer is in radians, it will not be labeled that way. So if you're talking about an angle, if it's got the little circle on it, that's how you know it's a degree. If it doesn't have the little circle, you always assume radians. Okay? So let's convert 45 degrees. Okay, so Tahina, where would degrees have to go here so I cancel it out? In the bottom. And what number do we always think of with degrees?
180.
That's your 180. And the number, Julia, that we think of with radians is pi. Okay, I'm going to stop writing RAD because you're not going to see that in the book. Right? You might see it occasionally when they're starting out with some conversions, but in the homework problems, they won't have it. So degrees cancels. And anybody think they can tell me my final answer as reduced as possible? Yep, what's that? Pi over 4. Good. Pi over 4. After a while, you'll probably know the multiples of 30 and 45 in your head. Right? If I asked you to convert 47 degrees to radians, you're not going to be able to do that in your head. It's a decimal. But 45s, 30s, and 60s, they come up a lot. So same approach here. Put degrees in the bottom, so it'll cancel degrees in the top. And somebody else tell me, what does that come out to?
Pi over 3.
It's pi over 3. We saw all those numbers in the program we just used. Right, and let's try 90. Multiply by pi over 180. Okay, and someone else, what's going to be my final answer there? Pi over 2. What's the unit? Well, it's not written, but it is understood to be radians. Yep. Okay, it's not written, but it is radians. Okay, any question on that? We'll try a couple with decimals in a second. Okay, so let's try some with the other way. Change to degrees. Now this time, if you want to think about the word RAD, it's written after pi. Okay, so that's in the top. So where would radians go in the other fraction to cancel it out? Yep, in the bottom. And what's the number we think of with radians? That's my pi. And where would the 180 go? On the top. Okay, so for the first problem, I'll write it out. So radians and radians would cancel. Okay, what else? Anything else that cancels? Yeah?
The 2 pi's.
Yep, pi and the pi. And anything else I can reduce before I multiply? Yeah. The 2 and the 180. 2 goes into 180 90 times. So you're left with 3 times 90. And the only unit left is degrees. So how many degrees would that be? 270. Does anybody remember from the ones we just did, pi over 3? How many degrees was pi over 3? 60. So double pi over 3 should be how much? Should be 120. Okay, we can go through. Multiply by 180. I want degrees in the top. I want radians in the bottom. So my units of radians cancel. Pi cancels. 3 goes into 180 60 times. And we're left with what we expected, 2 times 60 degrees, 120 degrees. Okay, any question on that? Okay, pi over 4. So when I'm doing this in my head, I don't go through this conversion a lot of times. I think, do I know, so I want to do 5 pi over 4. Do I know pi over 4? Okay, if I know pi over 4, and I can multiply that number by 5 in my head, then I've got my answer right away. If I don't, then I'll go through the conversion. Okay. So multiply, what's going to go on top? 180, and on the bottom? Pi. So my radians cancel, pi cancels. How about 4 into 180? How many times? 45. And that's the step I jumped to right in my head. I knew pi over 4 was 45. I just need to multiply it by 5. Okay, what's 5 times 45? 225. Okay. All right, let's try one where we round it. Okay, when you round it, just use your calculator, type it in, and round it off. Generally in the book, they will tell you when to round it. If they ever don't give directions, as a general rule, multiples of 30 and 45, leave them as pi. 500, that's not a multiple of 30 or 45. Anybody remember which way do I multiply by here to convert degrees to radians? What goes on top? Yep, pi on top, 180 in the bottom. Okay, this is just going to be an approximate answer. Take 500. Okay, use your pi button and divide by 180. So we get about 8.73 degrees. Okay, with a negative angle, it doesn't change. Doesn't change how you do anything. You'd still multiply by pi and divide by 180. Yeah.
Wouldn't that be
Oh yes, radians. Thank you. Converting to radians. Radians. Okay, so for negative 200, I just type in on my calculator, negative 200 times pi and divide by 180 and see what I get. Okay, again, I wrote radians here just so we kind of get used to not seeing it. Okay, so to convert, what goes in the top? Oh, Orlando?
degrees?
Yep, and what number?
180.
Yep, the 180. And in the bottom?
Radians or pi?
Yep, pi radians. So radians cancels out. This time there's no pi to cancel out. Okay, so just go straight across. 3 times 180, divide by pi. Okay, so that's 171.89. And that's degrees. Let me show you what happens if you don't use the pi button. Okay, I'm going to type the same thing. Do 3 times 180, that's 540. But then divide by 3.14. Okay, we get 171.97. That's quite a bit off. It's not like we got 0.89 and 0.88. That'd be pretty close. We got 0.89 and 0.97. All right, so if you don't use the pi button, it's going to throw your answer off. Sometimes quite a bit. Sometimes not as much. Okay, and 5.2 radians, you do that the same way. Just multiply by 180 and divide by pi. Make sure you use the pi button. Okay, any questions on that? All right, so let me put up the homework. Okay, the homework is, it's a lot of short little questions, like find an angle that's coterminal, change to degrees, change to radians, so that's why there's so many. But they're very quick. I don't think there's any problems today that'll take you more than 30 seconds a problem to do. Okay, so it's on page 323. It's 1 to 4, 7, 9, 11, 12, 15, 24 to 26, 30 to 32, 35 to 37, 41 to 43, 47, 51 through 53. Okay, so we'll take a look at that tomorrow, and we'll finish section 6.1 tomorrow.